Well, good morning, everyone. It's good to be with all of you. As we've been talking about breakfast, I hope all of you had a good, healthy start to the day, making sure that you began with the most important meal of the day, at least until lunch and dinner, and dessert. Um, so it's good to be back with you. Yesterday, when we were together, we were talking about alternating series, which are, relatively speaking, straightforward. I, I'm not sure whether we did enough examples for you to fully feel that, but I think when it comes time to start working through these questions, you're going to enjoy yourself perhaps a little bit more than you did with the integral test. So that's the alternating series. Today we're going to pick this up and spend a little bit more time on the alternating series and then transition into the ratio test, which should be fun. When we were last together, we ended by talking about the alternating series test, and we introduced this idea of absolute convergence. And so I'd like to begin by kind of picking up where we left off. So in that last example that we worked through, we had the sum from n equals 1 to infinity of -1 to the n minus 1 times 1 over root n. And we learned that if we took the absolute value here, then we would get a divergent series, which told us that the series is not absolutely convergent. But then we took the limit of the terms, and that told us, so this is using the alternating series test, that told us that since the limit of the terms was 0, it told us that our series was convergent by that alternating series test. And so that's kind of where we left off. And so we're going to begin today by simply introducing one more piece of vocabulary in this section. Again, we are in sections 10.6 and 10.7, about halfway through the notes packet, or a third of the way through the notes packet. So we have this definition. The definition is that a series is called conditionally convergent if it is convergent but not absolutely convergent. So it's yes, convergent, no, to the absolutely convergent. So going back to that example that we just looked at, is that series convergent or divergent? Well, we already learned that it's convergent. If it's convergent, is it conditionally or absolutely convergent? We learned that it was not absolutely convergent. So that previous example was conditionally convergent. One thing that should kind of jump out from this is kind of the following theorem, that if a series is absolutely convergent, then it's also convergent. So let me see if I can make sure this is clear. So convergent does not mean absolutely convergent. Here I have an implication, so I'm going to X my way through it. Does not mean that, but absolute convergence does imply convergence. Questions about that? Very good. So let's look at example 4. We can do this using our DocCam. So we want to know, is this series convergent or divergent? And if it's convergent, is it conditionally or absolutely convergent? And so what we can do is we can look at this and we observe the n cubed in the denominator right here. And so that gives us a little bit of a hint of what's going on. And we think to ourselves, hey, maybe the p-test would be nice here. And so that let's try for absolute convergence. See whether it works. So if we want to figure out if it's absolutely convergent, we would look at the sum from n equals 1 to infinity of the absolute value, all that garbage. Absolute convergence. So we're taking an absolute value here, which gives us the sum from n equals 1 to infinity, 1 over n cubed. What kind of series is this, and does it converge or diverge?
P series.
P series, and does it converge or diverge?
Converge.
Converge.
It converges. Yep, it converges. So this is a convergent P series. So this tells us, therefore, the series that we were given converges how?
Absolutely.
Absolutely. You're absolutely right. Absolutely, which tells us that since it converges absolutely, that tells us that the series also converges. So it's like converges absolutely is the stronger statement, and certainly if you have the stronger condition being true, then you'll also have the weaker condition being true. Does that make sense? So let's look at this in the little flowchart thingy. So if you think about this in terms of a flowchart, what we are doing is we're testing these infinite series, and there's the two options. Does it diverge or does it converge? If it's convergent, it can converge one of two ways. It could converge absolutely, or it can converge conditionally. In this last example, we had a series that we discovered converged absolutely, and in order to get here to absolutely convergent, it must have also been convergent. So perhaps that will help you see kind of the flow of these choices. Questions before we go on? Very good. All right, so we're going to transition here, and the thing that we're going to talk about right here at the outset is we're going to talk a little bit more about estimating error bounds. I think there was a question on the last assessment where you had to do something around estimating an error bounds or remainders, and it can get a little bit you can get a little turned around there if you're not careful. But this is a relatively straightforward place to do estimating and error bounds. So let's see what happens. All right. So recall that if a series converges to a value s, then the remainder, Rn, equal to s minus Sn, where Sn is the sum of the first n terms of the series, such that the magnitude of the remainder is the absolute error in approximating s by Sn. So an upper bound on the magnitude of the remainder in an alternating series arises from the following observation. When the terms are non-increasing in magnitude, the value of the series is always trapped between successive terms of the sequence of partial sums. And so what I want to point out is that the remainder is this amount here. The remainder the remainder is the distance between the dotted line S and whatever the partial sum is. Okay, so maybe another remainder would be like right here. Okay, and that remainder, or at least its magnitude, is always less than or equal to the distance between the consecutive terms. So here's the Sn dot, here's the Sn plus 1 dot, and so the red length is always less than or equal to the green length, and that green length is equal to An plus 1. So we get that the absolute value of Rn is always less than or equal to An plus 1. Super nice, convenient formula. If I was to write this in words, again, I would say that for alternating series, the remainder is less than the next term out in the sequence. Questions about this picture? Very good. So that gives us the following theorem. So the theorem for the remainder in an alternating series. So we're given this series here. So series from k equals 1 to infinity of -1 to the k plus 1 times ak. Remember that those ak's are always non-negative. And so the -1 to the k plus 1 is what makes it an alternating series. So let this thing be a convergent alternating series with terms that are non-increasing in magnitude. Let the remainder be given as follows. Then the magnitude of the remainder is always less than or equal to the next term out. In other words, the magnitude of the remainder is less than or equal to the magnitude of the first neglected term. So we can do this, we can show how this works in the following example. All right. I believe yesterday we talked about how if we evaluated the alternating harmonic series, that if we evaluated that using some of our power series techniques, we would find the total sum is the ln of 2. And so we might ask ourselves, how many terms of this series here on the left are required to approximate the ln of 2 with an error less than 10 to the -6th? I think yesterday Joseph asked me for an application, and I used this as one application. I said, you were on a desert island, you needed ln of 2, and this would be one way of finding it. So let's figure out how long it would take you to get a decent approximation of ln of 2. So what we want to know is, we want to know when is the remainder less than or equal to 10 to the -6th. Okay. And so got to ask ourselves, what is the remainder? So Rn is going to be less than or equal to the next term out. So if this upper limit here was for example, a 10, like an upper limit was a 10, then the next term out would have an 11 in the denominator. If this upper limit was 50, then the next term out would be with a 51 in the denominator. And so if we're going for n terms, then the next term out would be a 1 over n plus 1. Which, by the way, is different than my notes. I lost track of the plus 1 in my notes. Questions about where the 1 over n plus 1 came from? Very good. And what we want is we want this remainder to be less than or equal to 10 to the negative sixth. So now we just need to solve. So we get 1 over n plus 1 less than or equal to 10 to the negative sixth. 10 to the negative sixth is less than or equal to n plus 1, or 10 to the plus sixth. 10 to the plus sixth minus 1 is less than or equal to n, which 10 to the sixth I think is a million. So I think this is saying 99999 has to be less than or equal to n. So what this is telling us is that to approximate ln of 2 within 10 to the negative sixth, we need near about 1 million terms in our sum. Wow. That's interesting. I would say, going back to the desert island, that technique would be valuable if your goal is to fill your days. I think there's got to be better ways of calculating the ln of 2 than this particular series, but it would work.
Gonna have to be on that island for a long time.
Yeah, exactly. By the time you actually get ln of 2 to whatever precision you need, you'll probably have long forgotten why it was that you were doing these calculations. So it'll work. Can you imagine your common denominator? It'll be quite an experience. So questions about doing error bounding or remainders with alternating series? Very good. All right. So we're going to shift gears. We've been talking about the alternating series test, and I want to transition into section 10.7, same set of notes, but section 10.7, and focus in on what's called the ratio test and then also the root test. So let's start by doing this by looking at some of this COVID data that a few of us have been tracking on Fridays. So when trying to understand exponential growth, one tool is to look at the growth rate. So some of you have tracked along with our COVID data, others haven't. What I did was I went through last week when I was playing with these notes, and I grabbed data from the Washington Department of Health every week. So I grabbed data on March 1st, March 8th, March 15th. So this is the number of cases that are in Washington state on the given days. And so you'll notice that last week there were about 13,000 cases in Washington state. And then we asked ourselves, what's the growth in cases each week? And so notice that in that first line, we went from 30 cases to 245 cases, which was a growth of 215 cases in the week. The next week, we went from 245 to 921, or a growth of 676. And then if you take 676 and divide by 215, you'll get the number that sort of looks pi-ish as the ratio of the growths. For those that have been tracking on with me on Fridays in those discussions, you might say, boy, these numbers look kind of different than what we've been looking at before. The reason why this is different than what we looked at before is because here I'm looking at weekly growth versus daily growth. That's the shift. But anyway, if you think back to that very first video that we watched, how do we know when the pandemic shifts from growing exponentially to flattening off? What's the ratio that we're looking at or looking for?
1 or below.
Yeah, so, well, it's not 1 or below, it's below, right? So when the ratio equals 1, that's inconclusive, right? When the ratio is bigger than 1, this is bad. And when the ratio is less than 1, well, it's good, or at least in this case, it's gooder, right? I don't know if gooder is a real word, but for our purposes, it is. And so you can see that in the beginning, for those first 4 weeks, we had ratios that were bigger than 1. This was bad. Now here for the last 3 weeks, it's been below 1. That's gooder or good. But we also noticed that it was at 1.05, which was close to 1. Now it's at the last time we had the data was at 0.93. Those numbers are kind of close to that 1, which is a little bit harder to interpret, right? And so putting this together, we have that ratios that are over 1 indicate continued growth. Divergence, in the case of COVID, that's very bad. Ratios under 1 indicate the growth is slowing, and convergence, which in the case of COVID is good. The ratio of exactly 1 is inconclusive, leaving the possibility of either convergence or divergence. Does this make sense? Kind of looking at the data and how there's these 3 possible cases. So for those of you that have been tracking along, or maybe you haven't been a part of the conversations, I might encourage you to join us tomorrow as we continue to look at the data. So what would it be? March or May? What's 7 days from the 26th? The 3rd, I think. Is it the 3rd?
2nd of June.
Well, it won't be June. That I'm positive. 30 days in September. Yeah, this is the complicated date math. 2nd or the 3rd?
For May?
2nd.
Yeah. What's the next
May
one?
3rd.
May
If
3rd.
we're looking at the next month, it's the 2nd, but May 3rd is a week after April 26th.
Thank you.
Oh.
I'm terrible with.
Right.
I have a hard time with calendars. I got to actually look at them. Should we take a sidetrack? I mean, May 3rd's already passed. Should we figure out what that ratio is? People like to know what's going on.
Yes, please.
Sure.
They opened up the parks. I
Yeah,
want to see it. I don't want to see it, but I want to see what number it is.
Let's see if we can figure that out. I didn't open the stuff ahead of time, so forgive me for having to pull things up in front of you. I'm just trying to find the link. I can't remember what the site is. I think I have it listed here on the tab. Come on. Still loading. Aha. COVID in Washington. Here's our website we're working on. All right. Boom, boom, boom. All right, so our question is how many cases were there on May the 3rd? So what's that ratio going to be on May the 3rd? Parks are open. I think I told you that I walked down to Saltwater State Park. Enrique saw me. He was gracious. He didn't run me over with his car. So that was good. Man, as this stuff loads, interesting thing, I was at an interview yesterday and for this vice presidential role. And the crazy part is one of the guys we interviewed was, I was part of the group that hired him 10 years ago for an internship at Highline. And it's pretty crazy to think that this guy that was a teaching intern 10 years ago is now applying for a job to be a vice president. Yeah, pretty cool guy, really neat guy, but still. Current status. Where was it? Does anybody see it by the dates?
Did they?
Aha, this is the one.
Sweet.
They changed the website for those of you that haven't been a part of it. So, like, what's going on here? So, 5.3. I don't know if you can read this. So, 15,482. That's what it was on 5.3. So let's go back to our notes and see what happens. So we want 15,000, and I just wrote it down, 15,482. That's how many cases there were on 5.3. Can somebody, you got your texts and friends out, can you tell me what this growth is? That looks like 1,000 what?
I confirm.
I'm just going deaf. 1,700 what? 58. Okay. Notice that's more new cases than the previous week. So this is going to be a 1 point something. Okay. 17. 1.009. Like that. Does that line up with the data that you all had seen? So that's not good. That's not good news. It's not terrible, but I mean, that's the highest it's been since the beginning of April. And even though the numbers aren't well, what that means is it puts us back in the world of exponential growth versus kind of that flattening off part of the logistic curve. So for those of you that are wondering, why is the governor wanting us all to stay home? It's because, oh no, unfortunately, we switched over to the wrong place. Cool. That's pretty good. Everybody's coughing on their Benjamins. That's pretty good. Questions about this? So I share this particular example not so much because it has a direct connection to the ratio test that we are going into, but rather because I think it's a good example of all the cases that we are about to see. So it's an analogy, not a direct connection. So here's how the ratio test works, and probably most of you have played with the ratio test in Calc 3. So if the limit of the terms, limit of the ratio of the terms is less than 1, then the series is absolutely convergent. We like this one. This is happy. Think COVID's going away. If the limit is bigger than 1, then the series diverges. Think COVID's expanding. That's bad. Oh my gosh. Nice stuff in the chat. And then if the limit is equal to 1, then the ratio test is inconclusive. Like maybe it converges, maybe it diverges. We just don't know. So I'm not asking you, just to be clear, I'm not saying that the COVID stuff is using the ratio test from Calc 4. Rather, I'm saying that the concepts or the conclusions kind of parallel. And so I think that the COVID example is a good way of remembering what's going on in the ratio test. Questions about this? Very good. Well, let's knock out a couple of examples. I think that's where we're at. Oh, before that, let's look at the list again. I think it's important to stick with the list. So we have now gotten up to 11 items on the list with the addition of the ratio test. Ratio test tends to be relatively easy and powerful. It's one of our favorite kinds. And we'll, on Tuesday, we'll talk about what the best tests are to use and when to use them. But at the moment, we're getting to probably the best test that's out there, maybe limit comparison test being number 2. So let's do a couple of examples, beginning with, it says it's example 5, but it's actually example 6. All right. So when you see powers or you see factorials, these are an indication that you should consider using the ratio test. So to use the ratio test, we'll look at the limit as n goes to infinity of the absolute value -1 to the n plus 1 times 2 to the n plus 1 over n plus 1 factorial, all over -1 to the n, 2 to the n over n factorial. These absolute values here help us because they immediately knock off what part of this ugly expression?
The alternating part?
Yeah, the alternating part goes, we hope, the way of COVID. Okay, and so this will be the limit as n goes to infinity of 2 to the n plus 1. Once you've done this a few times, feel free to write a few less steps. Which simplifies to 2 to the n plus 1 over 2 to the n is what?
Two.
2, right? So that's 2. And then n plus 1 factorial over, sorry, n factorial over n plus 1 factorial is
N plus 1.
n plus 1. And the limit as n goes to infinity of 2 over n plus 1?
0.
0. Now, let me just switch back for a moment to the list. So notice that we just got that the limit is equal to 0. Let's think about all the things that 0 can mean. Like, what does 0 mean if we're in the context of the geometric series? Well, it means that it converges. 0 does not apply here. 0 does not apply to the telescoping series. 0 doesn't apply to the integral test. Test for divergence, what would 0 mean?
Inconclusive.
Inconclusive.
Inconclusive, good. No meaning in the P series. If it was in the comparison test, it could mean potentially that something converged. Maybe a 0 would mean that. Limit comparison test, what does it mean? In general, this tends to mean that means you're inconclusive. You chose has a bad comparison. That's what it generally means. Alternating harmonic series, it could mean that it converges. Alternating series test, the same thing, the ratio test. So the deal is that it can get really tempting to try to memorize what 0 does, but I guess I would point out that 0 means different things in different contexts. 0 has how about this, more than 1? I like that. one interpretation. So be careful. I'm trying to give you a warning of things that seem like they trip up students. So don't think about zero in general. Think about it just in this context in terms of the ratio test. Back where we were. In our context, what's important about zero?
That it converges?
There's something really special about zero. It's
Less than 1.
It's less than 1.
Less than 1, okay.
Yeah. Since it's less than 1, what does that tell us? Now you can go, Enrique.
That it converges because it's less than 1.
Yeah, so this tells us that the series,
And because it's in the absolute value, it's absolutely convergent, therefore convergent?
converges absolutely. Using which test?
Ratio test.
By the ratio test. Yep, exactly. Questions about that? Did you guys do a lot of examples with the ratio test in Calc 3?
Yeah, this looks pretty.
Pretty straightforward, yeah. Cool. So let's look at the next example, and the purpose of the next example is to say, don't be too much in love with the ratio test. Okay. So before we start doing all kinds of crazy writing, this series on the left, does it converge or diverge, and how do you know?
It converges because the P series is the exponent's greater than 1.
Yeah, this is a P series, exactly. How about the one on the right, convergent or divergent?
Divergent. If you take the limit, it'll go on to infinity.
Yeah, I mean, these terms are 1, 4, 9, 25. They're getting out of town in a hurry, right? So we know without doing anything complicated that the one on the left converges. And we know the one on the right diverges. So let's try the ratio test. Not because we don't know the answer, but because we're trying to find the power and limitations of the ratio test. So if we look at the one on the left, maybe I'll call that A. So we looked at the limit as n goes to infinity. I'm going to ignore the absolute value because there's not much to do with it. 1 over n plus 1 squared over 1 over n squared, which would be the limit as n goes to infinity of n squared over n plus 1 squared. What's this limit going to be?
1.
What is that? What does 1 tell us? Yeah. Damon, it's example 6 in the notes, except for I have 2 5s. So it's example 7.
Thank you. Just making sure. Thank you.
Yep.
So it's conclusive.
So it tells us it's inconclusive, right? Do people know what the word inconclusive means? Can somebody make sure they define that?
Reach the conclusion? There's no answer? It's like up in the air?
Yeah, it's still up in the air. We don't have an answer. There is no conclusion. It could converge, it could diverge. So in the case of A, we got inconclusive. In the case of B, I think you can probably already see what's going to happen. So we're going to end up with n plus 1 squared over n squared for our ratio test, which is also going to be 1 and inconclusive. So, short question, does the ratio test work on these two examples?
No.
No, it's inconclusive. And so pro tip is that the ratio test fails with which kind of series?
P series.
P series.
Fails with P series. Or things that are like the P series. What kind of test works really well with things that are like a P series?
Integral?
Even easier than that.
The limit test.
The limit comparison test. The limit, if you have things that have a P series in them, the limit comparison test is your friend. If you have things that have factorials and powers, then the ratio test is probably your friend. If you have combinations, well, maybe you have no friends. I don't know.
Did you say that we
Figure
were
it out.
going to go over more of this next time once we have them all, see which one's better? Just what you said?
Correct.
Okay.
Correct. We'll pull them all together, I think on Tuesday. Questions about this? Okay. Whew. I think what I would like to do, we just have a couple minutes left. I think what I would like to do is walk quickly through my notes on the next example. I think it's the next example. And then we will repeat this next example on tomorrow. But I think that if we go through it today and you see it again tomorrow, I think that that will help you to digest what's going on. So let's go back to the shared notes. So in this particular example, I think it's example 8b. I think that's the one that we're up to. We have the sum from n equals 1 to infinity of n to the n over n factorial. And we're going to try to use the ratio test. And so when we try to use the ratio test, we end up with the nth term, this stuff here, which is an plus 1 divided by the stuff over here, which is an. And we mess around with things simplifying. And when we simplify, we end up with the limit as n goes to infinity of n plus 1 over n to the nth power, which would be the same thing as 1 plus 1 over n to the nth power. And we have a limit out front. So as n goes to infinity, what is the base approaching? As n goes to infinity,
1 plus 0? Or?
1 plus 0, which is 1. And the exponent is approaching
Infinity.
infinity. And so we're approaching a 1 to the infinity, which is what?
Divergent.
So if it is a summation, then it would be the n. It would be n, but in the case of limit, it should be just 1.
It is a limit, but we're approaching what happens when a limit approaches 1 to the infinity? We say it's a
1.
no,
Indeterminate form.
it's an indeterminate form. And when you have an indeterminate form, what do you have to use?
L'Hopital's rule?
You have to use L'Hopital's rule, exactly. So we're going to have to use L'Hopital's rule, but L'Hopital's rule requires that you have what? It requires that you take a whole bunch of derivatives. And in order to take derivatives, you need what kind of variable?
X's.
You need x's. You need a continuous variable. And so when we pick this up again tomorrow, what we will do is we'll work through the step-by-step from scratch. But I wanted to simply remind you of this idea of an indeterminate form, its connection to L'Hopital's rule, and the need for that continuous variable x in order to take the derivatives that we will be working with at the beginning of class tomorrow. Any questions about that? Very good. Very good. So thanks everyone for another good day. I appreciate all the questions and the chance to interact, and also the great jokes that you guys are always cracking on the side. I wish you all a wonderful day. Have a good time working through your homework. If you have questions, feel free to hang on the line for office hours. But in all these things, may all of our paths converge, and may all the COVID cases go to zero soon. So stay safe, everyone. I'll see you tomorrow.